Hey, this is Avi Gutman with another Ask Me Anything event brought to you by quantreasoning.com. I invite you to join me live next time. We do this every Saturday at 11 a.m. Eastern, and you can attend for free by starting your free trial at quantreasoning.com. So I have a very interesting data sufficiency question for us here that has there's a very long way to solve it, but there's also a very quick way to solve it. And I think we'll start with the long way just so that we can better understand the shortcut. So, but first I'll give you a minute or two to give it a try on your own. If we combine the statements, we know exactly how many cakes there are, and we find some solution to the question. There has to be at least one solution. I hope everybody realizes that. There's not, like, the information they provide never lies. So there is a solution such that some number times 17 plus some number times 19 equals 140, where the total number of cakes is 8. There has to be a solution, otherwise somebody's lying. And if you start substituting one $17 cake for a $19 cake, or vice versa, you'd be increasing or decreasing the total by $2 each time. Every time you substitute one for the other, you're going up by 2 or down by 2. So with a total of 8, and knowing that you're going to be going up the number line or down the number line by increments of 2, you quickly kind of see that there's only going to be the one solution. This is when we combine the statements. And we're going to use similar thinking when we look at just statement 2 on its own. But I think with combining the statements, it's super clear that you're not going to have more than one possible solution because of the integer constraint. Because you're gaining 2 or losing 2 each time you replace the more expensive cake with a cheaper cake or vice versa. So now I think we're ready to talk about statement 2 on its own. And this is going to be interesting. I'm going to show you the long way, and we're going to learn something from doing that. The question wants to know how many $19 cakes were sold. And we can start by wondering, well, what if all of them were $19 cakes? Is there a way to get to 140 just by using a bunch of 19s? And you'd probably think, well, 10 times 19 is too much. That's 190. What about 8 times 19, which I'll think of as 20 minus 1? Well, that's 160 minus 8 is 152. That's still too much. And if I start subtracting 19s one after the other, what's going to happen is my tens digit will drop by 2 and my units digit will go up by 1. Because you see, the way I'm thinking about subtracting 19 is that I'm going to subtract 20 and add 1. Subtract 20 and add 1. Subtract 20 and add 1. That's how I subtract 19. And that allows me to very quickly write down a bunch more possibilities. So the next would be 114. And again, I'm subtracting 20, adding 1. Subtracting 20, adding 1. Subtracting 20, adding 1. These are all the possibilities for the amount of money received from selling $19 cakes, given that the sum total was 140. And I should eliminate those first two because they were too big, they were too much. Now what I can do is write down next to each of them how much money would have had to come from the $17 cakes to give a total of 140. And you can write these down very quickly as well by, once I have the 7, I'm just going to add 20, subtract 1. Add 20, subtract 1. Add 20, subtract 1. So I'm going to be very quick now. It's going to be 26. Again, add 20, subtract 1. Add 20, subtract 1. Add 20, subtract 1. Add 20, subtract 1. And add 20, subtract 1. So the right-hand column would have had to come from a multiple of 17. Now, we know for sure that one of these numbers is a multiple of 17. How do we know? Because if none of them is a multiple of 17, that means that the question was lying. And the GMAT questions don't lie. Does that make sense? So I can tell without checking, I can tell that at least one of them has to be a multiple of 17. And when you look at all these numbers that I've circled, it's an evenly spaced set with a gap of 19, a constant gap of 19. And we're going up by 19 each time. 7, 26, 45, 64, 83, and so on, plus 19, plus 19, plus 19, plus 19. So here's my question to all of you. Since we know that one of them is a multiple of 17, in an evenly spaced set that increases by 19 every time, when is the next time on the number line that you'll get again a multiple of 17? If you already have a multiple of 17, and then you just add 19, add 19, add 19, how many 19s would you have to add before you find the next multiple of 17 on the number line?
19 times 17.
Yeah, it's the definition of LCM, least common multiple of 17 and 19. That's how far up the number line you'll have to go to find the next multiple of 17. Now, if we understand all of that, then this question doesn't require any pen and paper. Why? Because I know from reading the question and from reading statement 2, I know there exists at least one multiple of 17 inside of that list that I could. It's one of those things where you say, let's not but say we did. Like, I'm not going to actually write down the list of possibilities. Let's not but say we did. I know that if I were to write down the list, I'm going to find at least one multiple of 17. And I know that the next multiple of 17 would be how far away? Or what's 17 times 19? I know it's more than 140, so I don't actually need to write anything down. But just for our purposes, I would think of it as 17 times 20 minus 1, which is 340 minus 17, or 323. That's how far up the number line I'd have to go to find the next multiple of 17. Which means that there's only going to be one in the range between 0 and 140, which means the statement 2 is sufficient on its own, and I can see that without actually putting pen to paper, using the reasoning that I just explained. So, to recap, we have 17 and 19, which are two prime numbers, which means their least common multiple will be their product, and we can tell their product is going to be fairly large, certainly more than 140. We also know, just from the given information, that there is going to be at least one multiple of 17 that to be found when we start adding 19s from 0. There will be at least one multiple of 17 before we hit 140. I should say one multiple of 17 remaining, completing the range to 140. And we can tell that there will be only one of them, because the next one would be another 323 beyond that. Therefore, I can very confidently say statement 2 is sufficient on its own, and the correct answer is B. So the long way to solve it is to put everything on paper that I did here, and the short way is to say, well, let's not but say we did. Here's what's going to happen. I hope you also took away from this that if you want to put together an evenly spaced set that's growing by 19 every time, you can do it very quickly by adding 20, subtracting 1, adding 20, subtracting 1, adding 20, subtracting 1. It's a very quick way to be adding 19 over and over again. We do want to distinguish between having an integer constraint and not having an integer constraint in this type of question. When we didn't have an integer constraint last week, when we looked at the X kilograms of material A and Y kilograms of material B, there was no integer constraint. It was a similar kind of question, but no integer constraint. So there we drew a number line, and we looked at an infinite number of placements along that number line. Whereas when you have an integer constraint, a number line is not a very useful tool because it doesn't take into account the integer constraint. The most common mistake I see people making when there is an integer constraint is they use algebra. They call the number of cakes of this type x and the number of cakes of that type y. And then they build one equation with two unknowns, and they say, well, that's not sufficient because I have one equation with two unknowns. But they're failing to consider the integer constraint, because algebra doesn't really play well with integer constraints. And a table type solution like we had here with the columns, that's a much more appropriate way to solve a question that has an integer constraint. If the question was different, if instead of $140 it was $500, then I would actually have to look at each of these and ask, is that a multiple of 17? Is that a multiple of 17? Is that a multiple of 17? Find it, circle it, whichever one it is, and then add 323 to find the next one.
Yep, that makes sense.
Or just add 323 and see, is that going to be above 500 or not above 500? Hey, I'm just going to interrupt my own video for a moment here. If you're finding value in this video, please let me know in the comments below. And give this video a thumbs up. It really motivates me to keep uploading a new video every day. Alright, back to the video. It's really noteworthy that you've got 3 different lines that all share the same point. That's really noteworthy because it means that you've got 3 lines that all meet in the same spot. Now, if you had 2 lines that meet in one spot, well, that's not that interesting. That would happen anytime the 2 lines are not parallel to one another. Right? They'll meet eventually somewhere. But to have a 3rd line thrown into the mix, also meeting those first 2 lines in the same spot that the first 2 lines meet, that's incredible. That's really noteworthy. I think it's a bit frustrating that we have an unknown of A and an unknown of B in the first line and the 3rd line, respectively. But I rejoice when I see that the 2nd line is given to us in full. We can draw the 2nd line. Let's go ahead and do that. So in the xy coordinate plane, y equals x plus 6. So we have a slope of 1, which means that it's a 45-degree line going up from left to right. And the plus 6 means that it meets the y-axis at 6. So if I were to draw that line, it's going to look something like that. This is the 2nd line. Y equals x plus 6. Now, I don't know exactly where the point PR is, but it's somewhere on this line. And it's the point that the other 2 lines would be going through. Now, the question is looking for the value of B. So if I know where exactly the 3 lines meet, I should be able to find B, because I know the slope of the 3rd line is 3. Right? Y equals 3x plus b. If only I knew, I just need to know a point on the 3rd line, and that would enable me to solve for b, because I would plug that point into the y and the x in the 3rd line. Now, statement 1 on its own tells me everything I could possibly want to know about the first line. I can draw the first line thanks to statement 1. Now, if I can draw the first line, and I also have the 2nd line, would I be able to find the point at which they intersect? Yeah, I know exactly what the 2 lines look like, I can tell where they intersect, and then I would be able to find the values of P and R. Which means that statement 1 implies statement 2. If I know statement 1, I can infer statement 2 on my own. I don't need them to give it to me. Is the opposite true? If I knew the value of R, so that's the y-coordinate of the point at which they meet. So looking at our xy coordinate plane, if we knew exactly the horizontal line on which the 3 lines meet, would we then be able to infer the value of A? We know that the first line goes through -5, so let's say that this is -5, so that's, and the line goes, I don't know the slope, but it goes through that point, however way it goes. But if I knew exactly the height at which the first line and the second line meet, because that's what they're giving me in statement 2, they're giving me the height at which they meet, well, then I could figure out the slope, because I know the first line goes through -5 on the y-axis. So if I know exactly the height at which they meet, whether, if that's the height, or that's the height, or that's the height, whatever the height is, if they meet here, wherever it is that they meet, I can now infer the slope of the first line. So statement 2 implies statement 1. These two statements are inferentially equivalent, which means we can eliminate A, B, and C. This is either D or E. Now the question wanted to know the value of B. Would we be able to figure out what the third line looks like if we knew where all three lines meet? Yeah, if I knew where all three lines meet, I could put R into Y and P into X, and I have the 3 there, and then I can solve for B. So each statement is sufficient on its own, and the correct answer is D. I don't know whether the first line looks like that, or looks like that, or looks like that. And there's an infinite number of ways to draw that first line. I don't know what it looks like. But if I did know what it looks like, then I'd be able to find the value of P and R. So if I knew exactly what the yellow line looks like, then I'd be able to calculate exactly where it meets the second line. Because we know what the second line looks like. If I know the value of P and I know the value of R, can I find the value of B, which is what they're asking about? Yeah, the value of P would go into the X, the value of R would go into Y, and then you can solve for B. So with statement 2 on its own, we no longer have all of that stuff. So we don't know all of the yellow stuff. But we do know, with statement 2 on its own, that the 3 lines meet at this height. So what I drew there, continue that all the way up there, this is 17. Y equals 17 right here. Orange line shows us exactly where the 3 lines meet. They meet, well, not exactly where, but they meet somewhere on this orange line. That's what statement 2 tells us. But we know what the second line looks like, so they must meet right here. So now I know the values of P and R, or I could find the values of P and R. And algebraically, you could plug the 17 into here and solve for X, and the X would give you the value of P. Interesting question, this one, right? So they're asking, in a certain list that has more than 2 numbers, is each of the numbers in the list equal to 0? And I think that the word each is really interesting, right? What does that mean for each of the numbers to be 0? That means all of them are 0. That's an interesting choice of words there. Is each of the numbers in the list equal to 0, meaning are they all 0? It's a yes-no question. So there are more than 2 numbers, and any combination of 2 numbers out of the list, so regardless of which 2 numbers we choose from the list, we're always going to get a sum of 0 in the case of statement 2, or we're always going to get a product of 0 in the case of statement 1, regardless of which 2 numbers we choose from the list. Any 2 numbers. What can we infer from statement 1 with regards to what they're interested in? Right? They want to know, are they all 0? I guess I would ask, first of all, is it possible that they're all 0? Does statement 1 allow for the possibility that all of the numbers in the list are 0? Yeah, it is possible that they're all 0. Is it possible that at least one of them is not 0?
Yep. You can have all of them be 0 except for one of them. and the product of any two will still be 0.
Very, very nice, Parth. That's right. So if only one of the numbers is non-zero and all of the others are 0, it would still be true that any product of any two numbers you choose is always going to be 0. And the reason is that in order for a product of two things to be 0, you only need one of them to be 0. The other one doesn't need to be 0. So as long as you only have one non-zero number, any product of any two numbers will be 0. So it is possible to get a no. Statement 1 is not sufficient on its own. Let me repeat again what I said. If you only have one non-zero number in the list, meaning all the other numbers in the list are 0, then statement 1 still holds. It is still true that any pair of numbers you choose will give you a product of 0. So statement 1 is not sufficient on its own. What about statement 2? The sum of any pair of numbers is always going to be 0, regardless of which pair you chose. For that to be true, they all have to be 0. In the minute you make one of them non-zero, then you'd have to make another one the mirror image of it, but there's more than two numbers in the list. So what would happen with the third number? You'd have to make it the mirror image of, well, you can't make it the mirror image of both of them. A number line is one-dimensional. So just to illustrate the point, let's say one of them is 2. Okay, so then another one would have to be -2 in order for their sum to be 0. But what if you chose that number with some third number? Well, that other third number would have to be 2, but then if you chose those two, you get a sum of 4. So the only way you're going to be able to say that regardless of which pair of numbers you choose, the sum will always be 0 is if they're all 0. And that's the significance of the more than two numbers in the list, because if there were only two numbers in the list, you could have 2 and -2. But with more than two numbers in the list, you're going to have at least a third number in the list. And what do you make that third number? Do you make it 2 or do you make it -2? Well, I don't know. It depends which one you want to add it to. And we don't know which one we want to add it to because of the word any. Any two numbers. The sum of any two numbers in the list has to be 0. Well, then they all have to be 0. It's the only way. And therefore, the correct answer is B. If you found this video useful, go to quantreasoning.com for a lot more where that came from. You should also click that like button and let me know in the comments below what you'd like me to make future videos about. And of course, if you haven't yet subscribed, go ahead and do that and click that bell below so you get notified about future videos. See you next time.